Welcome. Wow, thank you. That's quite the turnout. It's really cool. We're here to discuss some nitty-gritty details about how to develop, how to write code, which is kind of confusing given the keynote and everything that's happening with AI. I might be the person teaching you how to, put new shoes on your horse right as the car is being shipped. So I'm glad that you're all here. My name is Nicolai Parlog. I'm a Java developer advocate for Oracle, and I'm here to talk to you about data-oriented programming. And let's dive right in. You can see the slides online already. If you go to slides.epafx.dev, you'll see them on the right-hand side. If you scroll down a bit to find this talk. This talk is structured into 3 parts of very unequal length. The first part is, what is data-oriented programming? I'll give you something of a definition/explanation that will be utterly useless, but without some meat to put on those bones, which is what most of the talk will be about. I'll give you a long example. We're going to go through a made-up code, or through a made-up app that uses data-oriented programming. I'll show you how that works, what that looks like, and then at the end, we'll have a little bit of a reflection there. Okay, so what's data-oriented programming? Before we go into that, let's talk about what these programming paradigms are in general. Functional programming, object-oriented programming, structured programming, all of these. And in general, the goal of any of these programming paradigms is to manage complexity in some way, shape, or form. And complexity comes in a lot of different ways and shapes, and not all paradigms handle all kinds of complexity equally well. There are some things that are clearly superior than others, like structured programming, which was, basically we don't use GoTo anymore, like back in the 60s or 70s when that came up. I think it's fair to say that that is just better than what was there before. But when you compare functional programming to object-oriented programming, for example, I would posit that none of them is clearly better than the other. It depends on a lot of circumstantial facts whether one is preferable, not least of which, what are you more used to, but then also what is the problem area that you're working in. So it depends because different things or different paradigms are good at different things. And just to recap a little bit, object-oriented programming, you can kind of make up this tagline, everything is an object. It's not quite like that, but I think it's a fair summary. And combines state and behavior into units of code, right? You have a class, for example, that has state and has behavior that might change that state. It hinges on encapsulation, where a lot of that state and some of the operations you don't want to expose to just everybody. And in general, you implement polymorphism through inheritance. And all of these mechanisms work together to work really well when defining or upending boundaries. A boundary between large subsystems, a boundary between you and your dependency, a boundary between across different versions, boundaries for security. For all of those, object-oriented programming is really good. The first part is what I just said, boundaries between libraries and clients and large programs. And I want to propose to you to consider data-oriented programming not in those circumstances. So don't start out with, I have this big problem that I need to solve. Let's do data-oriented programming because I watched that talk. I want to propose to you, if you want to try this out, try to use it in smaller subsystems, so that are relatively isolated from the rest of the system, or maybe just that is the whole system, maybe just a small thing that you're writing code for, a small tool maybe. And the more that tool or that subsystem is focused on just data, the more you can envision it as just data flowing through it, the more sense it makes to use data-oriented programming. There are guided principles. Brian Getz, who's Java language architect at Oracle, formulated them in June 2022. And I was blasphemous enough to give a slightly updated version 2 years later, where I changed a few phrases and moved a few things around. The basics are all the same. It's just highlighted differently. And I asked Brian whether it's OK to do that. And he said yes. So I got his green light there. So this is version 1.1. These are the 4 guiding principles of data-oriented programming. Model data immutably and transparently. Model the data, the whole data, nothing but the data. Make illegal states unrepresentable. And finally, separate operations from data. And if we had a 5-minute lightning talk, I would say, and that's the talk, thank you, goodbye. And this is what I meant when I said this is kind of borderline useless, because that sounds great, but what does it look like in practice? And that's what we're going to spend most of the remaining time on. We're going to look at a lengthy example to go through what all of these guidelines look like in practice. Okay, I have a little demo application here that does actually exist. You can find it on my GitHub, which is crawling suitably GitHub. So the idea is you give it a link to a ticket, maybe to an issue or to a pull request, and then it will connect to that URL, identify what kind of page it is, looks for the interesting section, meaning not the header, not the footer, just like the conversation, identifies all outgoing links, and then goes back to step 1, right? So it crawls, starting at a GitHub issue, say, it crawls the links, and the way it's implemented is it stops at external pages. If you link to Wikipedia, it's going to look, oh yeah, that site actually exists, but it's not going to crawl further from there because you don't want to crawl the entire internet. And you can give it a depth, like only do it like 7 steps deep, because otherwise you might end up crawling all of GitHub, and that's not great either. Okay, so very simple tool. This is what it does. I clearly developed this before AI was a thing, because otherwise this could probably have been generated. But still, it's good because it's isolated and small, so we can discuss it well here. The whole crawling of connecting to the URL and pulling the page and all of that stuff, that all happens within this load page tree method, and it doesn't matter to us. Just mechanics. What I want to talk about here is the design of this, and specifically, what does this page type look like? So after I load like a page tree, I get back an instance of this type page. What is it about? What does it look like? Let's design it. Here are some requirements. First of all pages have a URL. And then if the page didn't resolve, there's an error. Maybe it was a 404 or maybe some other thing. It's one of an error. If the page did resolve, we want to get the content bed. That is like the conversation, for example. And then if it is actually a GitHub page and not a Wikipedia page, for example, I want to gather the outgoing links and I want to identify the issue number or the pull request number. And for now, we're going to pretend that GitHub has no other pages except issue pages and pull request pages. So that's some state, some data that these pages need to carry around, but they also might want to do stuff, right? If you have a page and then it's connected to other pages, you can see that as a graph, or maybe if you squint a little bit as a tree, and you could display this as an interactive graph, right? Maybe you want to compute some graph properties on that. You can categorize the pages by topic, you can do mood analysis, and if you offer all of those services, maybe you process payments for these. These are all like very disparate operations. Oh yeah, none of them are actually implemented because those are hard. What I did instead was this: evaluate some simple statistics and print a pretty string. But what I'm saying here is, imagine all of those operations that I posited before would be implemented, need to interact with pages. How would you implement them? And one way to do this would be, well, this. We just make it a type, make it a class probably, and we have accessors. You could call them get URL, but I didn't like that already before records were a thing. Get URL or just URL, error, content. As I said, maybe issue number, pull request number, and then all the methods down there, right? Basically, we take all the requirements and we dump it into the API of this one type. Even object-oriented programming, you probably won't do this because clearly this has issues. Maybe the underlying issue, that's not immediately obvious, but drives many of the other problems, is that the type of page I'm seeing is very implicit. Well, what is it, like an actual page that I connected to, or is it just an error? Is it a GitHub page, and if so, which one? That information is present in the API I just showed you, but you kind of have to guess at it. You have to say, oh, well, I'm going to ask for the error, and if that one is, I don't know, null, I guess, then it was an error. So the API before had this problem that the type of page was not really visible. And as a user of that API that doesn't have the domain just stored in his head, his or her head, the lead combination of fields is unclear. The fact that I can never have error and content kind of makes sense, but the fact that I can never have issue number and pull request number only makes sense if you know how GitHub works. And now imagine this isn't GitHub, which all of us know, I guess, but it's like a medical domain where we just don't know that as a developer which combinations is clear. So the clients that use this API have to kind of like figure out what kind of page they're seeing, and then on top of that, they have like all these different operations on there, right? I just put there only evaluate statistics and to pretty string, but imagine all of those operations were also on there, right? You now suddenly have a type which which has a lot of complicated operations as methods on it. That means that a lot of different subsystems collide in that. You've probably seen that these types which just grow and grow and seem to know everything. They know the database, and they know your email servers, and they know the payment subsystem and all of that. And we generally want to avoid that. Okay, so data-driven programming takes a different route here and says, okay, we want to make all data explicit and obviously correct. There should be no wait, which combination is legal? No, it should be immediately obvious. This is this, and that's that. Want to separate the operations from that data. So the operations do not live on that type. They live in those other subsystems, in the payment subsystem and in the canvas that draws these graphs. And then they just operate on the data. And then we want to model these systems as kind of a production line, right? As I said, envision this as data flowing through your system. You have different subsystems that do stuff. Maybe they transform the data even. So something goes in, comes out one of the subsystems, goes into the next one. And if you're thinking functional programming now, you're not far off. I'll get to that at the end of the talk. Okay, so let's do that. Let's apply data-oriented programming. Let's start with model data immutably and transparently. And we've got a language construct here that fits perfectly. Just in case you're an old Java version, it works with classes too. So that language construct could be, any guesses? What would be there to model data immutably and transparently in Java? Record, yes. Perfect, thank you. Maybe I should have gotten, you should have gotten up and do the squats and stuff. Maybe that would have helped. Okay, right. So yes, records finalized in Java 16. So if you're on 17 or 21, you're probably using records a whole lot already. For the few of you who don't, I will give you a brief intro. The idea behind records is, and that's from the JDK enhancement proposal, they are transparent carriers for immutable data, which sounds very suitable. The idea here is that unlike with a class, the compiler really understands the internal of a record and understands what its internal state is so that it can easily expose it, and it couples the API to those internals. And as a consequence of that, it reduces verbosity a lot. The goal with records is not, I want to write less code. The goal behind records is, I want transparent carriers for mutable data, and I get less code as a bonus on top. Okay, so let's say we create a record external page that has only the URL and then the content that we'll grab for that page, right? Let's assume somebody linked to Wikipedia, for example. What would I get then for this record? And as I said, if you've been using records, you probably know this, but for the rest of you, first of all, I get a type, which is basically a class with a few extra things, which is final. So I cannot extend it. I have private final fields for both components. These things here, URL and content, are called components. So I get a field for each of those. I get a constructor that takes both of those and assigns both of those. I get accessors. They would be called, some people call them getters, as I said. I don't like the get prefix anyway. So it's good that it's not present here. It's just URL and content are the accessor methods. And then I get equals hashcode and toString that operate on those. And basically all of that can be customized. So if you want to have a different equals, that's fine. If you want your accessor to do something, that's probably not a good idea, but you can do it if you want to. If you want your constructor to check additional properties, you can override it. That's all good. But you cannot remove any of those. You cannot say, oh, well, I don't want to have that constructor, for example. I don't want to have that accessor. Those must be there because they are transparent. And records do enforce or come with shallow mutability, meaning the record fields themselves can never be reassigned. But the record field can, of course, reference something that is mutable. And that's something you should fix during construction, because we want to model this transparently and immutably. We got the transparency. Let's make sure it's immutable. For example, having a different record here, the details are not that important. The important aspect here is one of the components is a set. And in general, Java sets can be mutable, right? So somebody could give me a hash set, and then I store a hash set in my component, and then if you get the hash set, you can still clear it, you can still add elements. And generally speaking, you wouldn't want this. By default, you don't want your record to do this. There are exceptions, and that's fair, but make it a conscious choice. By default, you should make sure that a record and whatever it references is immutable. And we can do this pretty easily. We go with a set.copyoff method, and I'm using what's called a compact constructor here, which is the constructor that gets. So the canonical constructor is the constructor that gets all the fields and assigns them, all the component as parameters and assigns them to the fields. The compact version of that just doesn't list the parameters and doesn't do the assignment explicitly. It does it implicitly. So after this code was executed, it will then after that assign all the fields. So what I'm doing here is I'm just creating a immutable copy, right? So we model transparently and immutably. Okay, then model the data, the whole data, nothing but the data. That was one of the guidelines. If we look at what data we actually want to deal with, those pages, we only have 4 kinds. there could be an error. If it's not an error, it could be either an external page, a pull request page, or an issue page. And that's it. That's all the things that we are willing to process. And data-oriented programming then says, great, just create one data type for each of them. There you go. You know, you could do the code that, for example, creates the immutable copy here, or maybe you want to check that the string or the URL are null. So there is stuff that you might want to check within those constructors or elsewhere in those records. But generally speaking, this would be the 4 records that you want to use there. And they just plainly contain whatever that data point has. And now the combination of legal states is obvious. All of these are legal and everything else isn't. So there is no type that, for example, contains an exception and content, because that wouldn't make sense for us in the first place. So unlike that class, this is straightforward. This is obviously correct, as I would like to put it. Okay. But we're not done yet. What we didn't express here is that there's more relationship between those data points. So we can say that when we try to load a page, it either works, it's either successful, or it's not. And if it is successful, it is either an external page or a GitHub page. And if it's a GitHub page, it's either a pull request or an issue. As I said, we're ignoring other pages that GitHub might have. So we have clear relationships between these that we can formulate as alternatives, as either or, as choice. And the way to model these is with sealed types. So if you are on Java 17, you can use sealed types, but I doubt that you did this a whole lot because they don't give you that much. Only once you have all the pattern matching stuff in 21 and later, does it really make sense to use sealed types. So I'm going to go over another little intro here. The idea here is that a sealed type limits inheritance. So before sealed types, you basically have 2.5 ways to structure inheritance. Either your type is open to extension by everybody, which is the default, or it's final, which means nobody can extend it. And then you can build some stuff with like, it's a package visible constructor, or it's a private constructor. So, it's not final, but extension is still complicated. So there's like a halfway where you can muddy around a bit. But generally speaking, those are the choices you had. No extension or free for everybody. And what sealed types do is they give you an option between those two, which is, yes, this type can be extended, but only by the specific types that I mentioned, and not by anybody else. And this communicates the intention not only to the compiler, but also to your colleagues, right? There's often situations where you think, oh yeah, so let's say we have a rendering pipeline, and we know we can only render, making this up, circles and triangles. Then it makes sense that your shape interface only has those 2 implementations. You don't expect the system to just work if you throw in, I don't know, ellipses, right? Probably you would have to update quite a few systems. If let's say you have a customer relationship management tool and you have like different types for different customers, you don't expect to just add a 5th type of customer and everything just works. Probably you have to go into the billing system to make sure that customer gets correctly billed. So there are a lot of situations actually where a type has implementations, but you are aware that an additional implementation is not just going to work, but that you have to update other subsystems. And a sealed type would communicate that. A sealed type would say, these are the implementations we know of. Those are the only ones that are allowed. Be aware that additional ones don't come for free, so to speak. Okay. But also, it allows the compiler to check exhaustiveness, something that becomes important later. Okay, let's do this now. Let's create a sealed type. We start with a sealed interface. You can also create sealed classes, but I'm going to ignore that option for this talk. We're going to create a sealed interface called page, and that permits 2 implementations, error page and successful page. And now only those 2 types can extend/implement that. And if I create a new type, like my page extends page, the compiler will complain. And the compiler will complain specifically on this line, like this part of my code would then be marked as a compile error, because clearly page does not allow this. Okay, now let's model those alternatives. We start with a page that permits either an error page or a successful page, right? Because that's the only 2 options that we really have. And every page has a URL, so we can actually use this interface to gather up some of the shared state that these different records have and expose them where they make sense. If the page load was successful, we either have an external page or a GitHub page, and all of those have content. And if it was a GitHub page, we either have a pull request page or an issue page, and all of those have outgoing links. And then there's a little bit of a subtree method that is not that essential here right now. The point I'm making is we create additional interfaces to model the rest of the data, the part that is not actually like data, but the relationships between them. And just in case you lost track a little bit, this is the diagram that we get from that, and in classic UML fashion, light blue is an interface and orange is a record. Pretty sure that's part of the standard. Go away. Let's hope the browser at the top will disappear sooner or later. Okay, so we have this interface here that is sealed, that only allows those two implementations, and so forth down. The interesting thing about this is, if you think about other UML diagrams about inheritance hierarchies, then this one is entirely sealed. There is no way to plug an additional type in here somewhere without causing a compile error. That is different from, for example, let's say you have the collection framework in mind, right? So there is list, and then there's array list, and there's linked list. And if you see a UML diagram of that, be aware that, of course, you can still add new list implementations, which is entirely intentional and good. But in this situation, we deemed it better to have it entirely sealed, and that means when I have a page, I know it must be one of those types. There's like no other option that the compiler will permit. Okay, it doesn't go away. Let me try to fix this. Huh? Come on. There we go. Great. Okay. Right. The third guideline was make illegal states unrepresentable. And a lot of those we already did, right? We already made sure that there's never a way that an error and content can collide in the same type, or issue and pull request number, or, all those other possible combinations. But there's still a lot of stuff that can technically happen, right? So for example, somebody could accidentally try to create an external page with a null URL, or with a null content, or with empty content, or whatever else we could come up with that we don't actually want our data that it shouldn't be like. And again, the default, you don't have to always do this to the extreme. There are situations where maybe you want to find errors later, so you have more information to report on that or something. But by default, you should make sure that your data model is 100% correct, so that you don't lug around faulty data and discover like late into the processing that, oh, well, I don't actually have everything I need, and then I need to abort. Okay, so everything that you do not want to happen rejected in a constructor. Where does that leave us? We now have the type of page that we have linguistically described enshrined in Java's type system, right? We have for every type that we have, we created a record. Only the legal combinations of fields are possible. The API is very self-documenting. I would argue that the API is clear to the point of being trivial, and so there's very little code to actually test. But what about the operations? Where did they go? The fourth guideline was separate operations from data. And that means record methods should not do fancy stuff. They should not talk to the payment subsystem. They should not talk to the canvas to draw themselves. They should not talk to the graph analysis toolings. They should really just, if anything, present the data that they contain in a slightly different form. Unfortunately for this example, the two methods that I picked actually do that, right? So the two methods that I wrote here should actually just be methods on those records, to be honest. But let's pretend that were not the case, right? Let's pretend they were more complicated so that I can show you something and how it works without having to come up with an actual complicated use case that doesn't fit on the slides. Okay, so let's now implement the operations on data. And the way to do this is to use pattern matching over these sealed types to then apply polymorphic operations, meaning operations that react differently depending on what type they're handling to their data. And since records are not encapsulated, that is straightforward, because that means that whatever data they contain is accessible outside of them, so everything can happen, right? With a class, you generally don't want this. A class is by default encapsulating its content, and so you don't want everybody from the outside just to rip it open and do whatever they need to do with the data in the class. A regular class, you want it the other way around. You tell it, no, I'm telling you what to do, and then the class itself, based on its own data, does its thing. Records are the other way around, so that's intentional. And the way to do this is with patterns. Again, if you're using Java 17 or 21, you probably already seen that, but I'll give you a short primer for everybody else. A type pattern does a type check, a cast, and declaration all on one line. It's not super common to do that in Java, but if you do an instance of check, you say, oh, is the root page an instance of the GitHub page? In the past, you would say, okay, then cast root page to GitHub page, and then do something. And a type pattern just in a very simple and straightforward way just does that for you. So it does the type check. Well, is root page an instance of? And if yes, it declares a new variable and casts the old one into that. That's very straightforward. And only, flow scoping means, of the term that we use here is flow scoping, only where this check is true is GH page actually in scope, right? So if there were like an else, or even without an else, even code outside of that if, is not able to access GH page because the variable is out of scope. Okay, I just said that, but that also means we can do fancy and tricky stuff. I'm showing you this because the code does contain it, and you can argue with your friends and colleagues over this whether that's good to do or not. What I'm doing here is I'm doing an inverted check. I say if the root page is not an instance of GitHub page, then return early, right? I don't want to deal with this now. But that means down here, if I made it past that return, then it was a GitHub page, right? And that means that the variable is actually in scope down here. So have fun with that one. But the more common use is not an instance of. The more common use is in switches. So since Java 21, we have the finalized feature where we can put those type patterns into switches, and we just say switch over the page, and in case it's a pull request, do this. In case it's an error or an external page, do that. And that's not how the implementation works, but conceptually, it just runs down this case statements and finds the first one that fits, and then executes what's on the right-hand side. And this is just prepared code that prepares the evaluate statistics part. We can skip it. You can look at it later if you have any questions about how this part exactly fits in. But this is the important part. This is where we evaluate a page. We gather some statistics. Specifically, we want to gather what kind of page it is. It's really simple. And we have these fields. We have a field, number of issues, number of pull requests, whatever. And we just want to increase the correct one, right? So this code is, again, easy to the point of being trivial, but I want to show you how this pattern matching is supposed to work. The interesting part is not on the right-hand side. The interesting part is on the left-hand side where we see, okay, so we get a page that we do not know what exact type it is, and that does not have a method that tells us how to evaluate statistics because we don't want to burden that type with that task. Instead, we have to evaluate the statistics ourselves, and the way we do this is, well, we ask what type it is. We figure out which type it is and then do the correct thing there. To pretty string, same thing. This is the setup. This is the actual code. And this one works a little bit differently because it actually returns the value that it creates. So again, we get a page. Again, we don't know what it is. The page doesn't know that if it's an issue, it should be a cat, and if it's a pull request, it should be an octopus. It knows none of that. It's just that something that we wrote, right? So we do the case, and then we take things apart. And here it actually becomes important that we use this variable. So only if it is an issue can we access the method issue number. Only if it's a pull request can we access the method pull request number. So here it really becomes important that we find out what type it is, because then we do something that we can only do for that type. And taking these things out with accessors is fine. Nothing bad is going to happen. But there's a better way to do it, and that is with record patterns. Record patterns were also finalized in JDK 21. And the idea here is that if you have a record that has these components, then a compiler knows how to access those, right? It knows that there's an accessor URL and an accessor content. So you can take those apart. You can say, if the page is an external page, then take this external page apart. I don't care about it on its own. I only care about what it contains. Take it apart. Give me two variables called URL and content, and assign the values to them. The important part about this is no reflection magic or whatever. It just calls the accessor URL. And if the accessor URL does something that it's probably not supposed to, there's not many reasonable things you can do in there, but whatever the accessor does would be executed so that your variable URL could be created here. And now we can do this. So for example, if we have the issue page here, we can say, okay, I don't care about the issue page itself, I only care about its content, and we take it apart into its 4 pieces, and we then only use one of them, which is a little bit annoying. We'll see how to do that better with unnamed patterns. But you can see how this would work, right? I only have 2 examples because the other one kind of like explodes the slide. But for example, the error page, I take it apart into URL and the exception, and then I only use, in this case, the URL variable. Okay, this is simpler with unnamed patterns, so let's have a look at that. Unnamed patterns are in preview in JDK 21, but they were finalized without any change. So if you are on JDK 21 and you want to use them and you feel brave, don't worry, you can just enable previews and then make sure that nobody uses any other preview feature probably. And you can use them. As I said, they didn't change. Okay, so what unnamed patterns give you is a number of different things. They all boil down to the underscore. In this specific context, you would just put underscores where you don't want to use something, right? So the GitHub issue page has like 4 different components. You only care about the one, and the other one you just underscore out, so saying like, I don't care. I don't need those. That makes it just much shorter and much more readable. And we can put all that together now, and it looks like this. And when you have this not on a slide, but in your IDE, then the whole arrow parts would be on the right-hand side, right? That would still fit in one line of code. And that it gives you a very interesting split in the code. If you look at only these case statements and how they pull apart these different instances, you will notice that they tell you very clearly what you're interested in. I'm interested in the issue page's issue number. I'm interested in the pull request page's pull request number. I'm interested in the external page's URL, and so forth. So the left-hand side tells you what you are doing or what you are interested in, what you are processing, and then the right-hand side does it. So that gives the code a more readable split than if you use accessors on the right-hand side, I would argue. Okay, so that looks good. But haven't we at some point learned in the past that these instance objects and switching over types, you could argue, is basically just a fancy way of an if-else-if chain with instance of chains? Isn't that icky? Like as an object-oriented programmer, it's fair if it raises the hairs on the back of your neck, like, I'm not supposed to do this, am I? Why though? Why is instance objects not something we want to do in object-oriented programming? And I'm asking for an idea here from you guys. No. Yeah, if you get more types, then something unexpected happens. Well, if you new type and you have like an if that checks for instance of types, and then the new type shows up, what's going to happen? I don't know. You just have to find the if chain and then check, I guess. Right. So it fails unpredictably when new types are added, which is not good, right? We don't want that to happen. But this is not the case here, because let me walk you through it. Let's say we add a GitHub commit page that implements GitHub page, right? It's Friday afternoon, and the product owner realized GitHub has more pages, comes to you, add the GitHub commit page now. Okay, so we add that. And now let's follow the compile errors, because we immediately get a compile error right here. Our record GitHub commit page with whatever components implements GitHub page, right? But that gives us a compile error because the super type is sealed. We said that earlier, so that's not going to work. So instead of this compile error sends us to the sealed type. And so we go here and we say, well, okay, our sealed interface GitHub page, which extends blah, 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 we now permit the GitHub page also. So we add a new type. And now the compiler is like, wait, you remember that UML diagram from earlier, right? Where they had like the page type on the left and then like these 4 orange boxes? There are 5 now. This isn't all the cases anymore. The compiler understands that this is not exhaustive, and it will give you a compile error. So I mentioned exhaustiveness before. I think it's time we look at that a little bit closer. An if-else-if chain does not need to cover all cases, right? You cover some cases you care about, and the rest just doesn't get a branch, and nothing happens. That is not true for a pattern switch. If you switch over a complex type, like not over number, but over something like a page, like an object, then you need to cover all cases. The compiler will force you to cover all cases. And there's only 2 ways to achieve that. One of them is to have a default branch, and the other one is to enumerate all subtypes. We did the second part, which is categorically the better default choice. But default branch can be helpful too, but in general, you should avoid it in these situations. Because we want those compile errors, right? If you have 4 types and then a default branch, then every new type will go into the default and the compiler is happy. But probably you want the compile error, so you pick 4 types and no default branch, and then if you add a 5th type, you do get a compiler on this new type. This is what would happen here. So the moment we change our, GitHub page interface to permit GitHub commit page, we get compile errors everywhere in our code base where we're not covering all types. And that's good, right? We want those compile errors. We want the compiler to tell us, this is where you now need to update your code to handle the new type. And we just do that. We just enter at the GitHub commit page, and the compiler is happy. So we said we want to separate the operations from the data. If you do that, you want to make sure that those operations are maintainable. And the way to do that is you switch over a sealed type, you enumerate all possible subtypes, and even if you have to ignore some, I'm going to show you in a second how, and you definitely want to avoid the default branch. Again, there might be situations where you want to have a default branch. What I'm giving you here is just like the 80-90% rule, and then there are exceptions. You're going to make a conscious choice, maybe add a comment Y, and that's good. Okay, and this way you get compile errors when a new type is added, which is good. If you do have defaulty behavior, like here, right? So let's say you want to have an emoji and only GitHub pages get emojis and everything else doesn't, you might be tempted to do this. That's a problem, because if you add the GitHub commit page, now it gets the NA, but you don't want that. You want the GitHub commit page, to have whatever emoji. So we want to avoid the default. One way to do this is this, which kind of sucks, which is duplication. Unfortunately, without unnamed patterns, this is what you're forced into. So if you do this on JDK 21 and you do not want to enable preview features, you're kind of forced into doing it this way. But you can use the underscore to combine branches. This does not make sense here. You cannot say case issue page issue or pull request page PR. And the reason why you cannot combine the first two branches is because, well, then you never know on the right-hand side, was it an issue or was it a pull request, right? It is one of those two, but which one is it? You don't know. So neither of those variables are reliably assigned, are reliably in scope. So that's why the compiler doesn't even allow that. But it does allow to combine branches where you don't name the variables, right? So you can say case error page, but I don't care what it is, or it's an external page, but I also don't care about what it is. So this is slightly longer than default, but it will get you the compiler error that you want. Okay, so what did we do now? We separate the operations from the data. We made it so that adding new operations is easy, but we made it also so that adding a new type is more work. Like adding a new operation just means, oh yeah, switch over page, case this, case that, blah, 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 do all the things, and then I'm done. If we add a new type, well, now we have to add the type, and then we have to go across all operations and update all operations. Note that this is the inverse of how it works with something like the regular inheritance hierarchy. Let's say you add a new kind of collection. If you add a new type, it's easy, just sit down, implement the interface, and you're done. But if you add a new operation, now you have to go across all types and add a new operation everywhere. So see how these are duals of each other, right? That's what I meant. Well, that's one example of what I meant earlier when I said that different paradigms are good at different things. If you frequently add and modify operations, then this approach is easier. If you frequently add and remove types, then the other approach, where you just have a regular inheritance hierarchy, would be easier. But that's just a small portion of the consideration, right? I'm not saying if you in one case do one thing, if you in the other case do the other thing. I'm just saying if you pick one of those two choices, be aware that there are trade-offs in this case. Also note that what I'm describing here is basically the visitor pattern, but less painful. The visitor pattern is the original object-oriented way to divorce operations from the type that they work on. And this has a lot of the same properties, just way fewer complications and indirections. And that was it. That was data-oriented programming given by a lengthy example. I have a couple more minutes that I want to use to go through a few odds and ends. And then after, you can either have questions here or probably better just come up after the talk and ask me, or I'll be around the conference, so you can ask me as well. Okay, but let's go through this. There's a couple of somewhat unconnected items that all connect to this approach though. So first of all, dynamic dispatch. Dynamic dispatch is a description of you want to invoke a method depending on the type. And Java has this as a language feature. You use this via inheritance, right? If you have a method called size on the list interface, and you call it on a specific type, then Java will find out, oh, which type do I have this method on? So dynamic dispatch works via inheritance, and Java just does it. But then that method becomes part of your API, right? If size is a method on the interface, then it now becomes part of your API. Everybody can call it. The visitor pattern also implements dynamic dispatch in a different way, but it also leads to the same result. Oh, I want to call this operation on this type. And the visitor pattern, as I said, re-implements this with the goal to not make it part of the API, which is good. But then the whole visitation part becomes part of the API. And also the visitor pattern is kind of cumbersome and indirect. And I have a little bit of a love-hate relationship with it because I worked in a software project for a couple of years where the visitor pattern was everywhere. And the annoying part about that is that was the correct choice. Like that is what the pattern was there for. It was the right choice to put it everywhere, but it was still annoying to see it everywhere. And then what pattern matching does is basically similar to that. It gives you another way to have dynamic dispatch to select which operation depending on the type. And the only way that you see this is basically that you want to make the type sealed. And then other than that, there's nothing visible on the outside on these types. And the implementation is pretty straightforward. Everybody can understand those switches. They're easy to read and write. So that means we now have a new way to do this, which formerly used to be a pattern. And I'm not sure, like I'm 100% subscribed to this idea, but sometimes people are saying, well, design patterns only exist because they make up a gap in the language. So if the language just does it, we just call it using the language. But if it doesn't just do it and we have to like jump through hoops, then it's a pattern. So for example, strategy pattern. Java, that used to be a thing, but basically every time you pass a lambda you're using that pattern, and at least I totally stopped thinking about it in those terms. It's just, I'm just passing a lambda. That's not a pattern. I'm just doing what the language offers me to do. And pattern matching does the same for the visitor pattern. So I think the visitor pattern will mostly go away, not entirely. It has a specific thing that it can do, namely internal enumeration, that the visitor pattern doesn't do out of the, that pattern matching doesn't do out of the box. But generally speaking, we replace most of those use cases and basically make the pattern go away because now it's just part of the language. Where would you want to do this or use this? I so far talked about like the big picture, basically a complex domain, even though the domain wasn't that complex. But there are other types, other situations where you can just start using this idea of a sealed type, which just exposes its information. For example, in a Hadoop data structure, in this code base, what I needed was a page type that is complete. The page instance is complete, but I didn't yet gather the outgoing links. I still need to gather those. So I just threw those two information together in a record. Fairly easy. And this time, I said earlier, you can deviate from these concepts, which is I want links to be mutable. I need it to be mutable because I want to add new links, right? So that's why I make sure that it is actually a hash set so I can add new stuff from the outside. So that means the idea of records and sealed types and pattern matching can also be used in a very ad hoc way when you just need a new type. For those of you who don't know, and I'm not saying you should do this, you can even define a type in a method. That is not new. You could always do that. It's bonkers to do it. With a record, still bonkers, but less so because it can be a one-liner. You can use it for more complex return types. Let's start at the bottom. Say you have a method called findUser that you give a username, and you get back a match. OK, that's an interface that's sealed, and these are all the implementations. You didn't find anything. You found an exact match, or you found a few fuzzy matches. So here's a collection of fuzzy hits. And to use this API, you would call findUser. You look at the interface match, which doesn't have any code. Like there's no method. So what am I going to do with it? Oh, but it's sealed. Oh, and I left out the permits clause because, first of all, I don't have it if it's in the same file. I don't have to put the permits there, but also, slides. OK, so how would I use this? I would use it like this. And I would argue this is supremely readable. Like, you call findUser, and in case it's none, you do this. In case it's an exact search, you do this. Otherwise, you do this. Like, it's hard to make it more obvious how to properly use this API. But you can also use this kind of stuff, as I said, in more complex domains, which is what I just did. Then, if you ever heard the term algebraic data types, this is what they are. Records and sealed types together form something that function programming fans call algebraic data types. And these two mechanisms, aggregation and choice, allow you to model a lot of things. They are really powerful in non-obvious ways. Once you start using them, it's hard to see, it's hard to stop. And I mentioned function programming as a couple times. I talked about immutable data structures, about methods or maybe functions that operate on them. Isn't this just function programming? And yeah, kind of. It's not that far off. The main difference is in emphasis, in what is the important aspect. Function programming says everything is a function. So you will focus on making reusable and composable functions. Here it's more about the data. And that means there are situations where it's either, this would be better for a better function, this would be better to have the data more well represented, all these trade-offs, right, in everyday programming. And basically they give you different guiding stars what to look for. But they are really similar in a lot of practical ways. But then also, I'm not here to tell you that, again, object-oriented programming is dead. It's still valuable for complex entities, rich libraries, for wherever you need encapsulation and boundaries. You have a large problem that you want to split into smaller problems. Object-oriented programming is really good for that. But if you mainly handle outside data flowing through, if you want to work with simple or ad hoc data, and if the data and the behavior specifically should be separated, then data-oriented programming is definitely worth a choice. Okay, quick summary that I'm going to skip in the interest of time. A bunch of follow-up links, videos, and also articles if you want to read. This is the original article by Brian Getz. This is my slightly updated series. The GitHub crawler is linked here as well. And with all of that, thank you very much for your attention.